Okay, so we are continuing with the discussion of estimators. So we are right now approaching the main topic of this course, linear minimum mean square error. This is called linear minimum mean square error, LMSE. Okay, estimation. So previously we have derived optimal estimators to minimize, let's say, to minimize mean square error, that is expected value of y minus, let's say, y hat, okay, mean square error, without any constraints on estimation, or let's say, okay, estimation function. So now we introduce parametric estimators and optimize over, actually this is more natural to us, because the other one, the earlier example, it was like in a general function class we are finding the best function, okay? But this one we are introducing parameter for this function class, and we will be just setting those parameters. Maybe we have very few parameters, then I can set those parameters by simply differentiation by calculus essentially, okay? So that's our goal. So how about this? We focus on affine slash linear estimators. So what do I mean by that? So for the first example, I am considering something like this, ax plus b, okay? So you see that this a is an unknown. These are two unknown parameters of the estimator. So obviously x is observation, y is desired random variable. So I'm just scaling observation by a, adding with b. So for the Gaussian case, you know, jointly distributed x and y, of course this is the optimal, but no, I don't know anything about, let's say, distributions. Then I'm only considering such an estimator family, affine estimators. Then I'm trying to find the optimal value of a and b, okay? So how can I define this optimality? Then the MSE under this constraint, under this estimator, for this estimator class, let's say, for this estimator class becomes MSE. So as you see, now we are working in a restricted, you know, setting. I'm not allowed to have an arbitrary estimator, but such an estimator. So y minus y hat of x, this is my MSE, where y hat of x is ax plus b, okay? So I'm left with this. Okay, so let's find optimal a and b values, minimizing MSE. And actually this is what we call linear minimum mean square error. Linear minimum mean square error estimation problem. Okay, because of, actually this is affine or linear. We are using this linear term in a somewhat like general sense at this point. but this is our goal. Okay. So how can I do this? Well, let me define my cost function j. Cost function j is expected value of y minus ax plus b parentheses square. Okay. So I'm expert in such minimizations. Why? Because I have only 2 degrees of freedom. So by taking the derivatives, I can immediately find the optimal a and b values, and this is what we are going to do. So let me write this as expected value of also e square. This is e square. So I would like to introduce this as e and so on, just to simplify my life. Okay, now step number 1, partial derivative of j with respect to a and equate to 0. Okay. So how should I do this? So this is expected value of a. This is expected value of, take this differentiation inside of, let's say, e square. E square is whole thing. Then expected value of, I have 2e. Then derivative of this e, let me write this e, maybe we can see it more clearly, ax minus b. Okay. So derivative of this e with respect to a. So I see minus a for this. So I get minus 2a expected value of. This is not correct. This is, if I take derivative with respect to a, I get minus x. Minus 2 times e x, and this is equal to 0. Okay. Let me write this bigger, and so on. So one more time, derivative of this e with respect to a is minus x. So I get this. Now, let me do the same thing for b. Of course, most of these steps are the same. This is equal to expected value, well, there is again minus 2 factor. Expected value of e, expected value of e times derivative of e with respect to b. So I get minus 1 for that. And I move the minus sign out, is equal to 0. Okay. So that is it. Now I have 2 equations, a and b, so I need to find the solution of these, join to solve these 2 equations. I can cancel minus 2's. So let me call this first equation. Let me call the second equation. Now my first equation becomes e times x. So what's e times x? Minus a expected value of x square minus is it b? B expected value of x is equal to 0. So this is e, I multiply by x, so I have yx minus ax square bx, that is it, is equal to 0. So my second equation, expected value of e times 1, so is it e times 1 is equal to 0. So I have expected value of y minus expected value of a times x minus b is equal to 0. 2 equations. So let me introduce some notation for this. Let me call this mx, okay? This is mx. Let me call this my, mean of x, mean of y. Expected value of xy, maybe let's leave it at that point. Or let me look at my notes. Okay, let's leave it as it is for now, okay? So I have A, B, 2 equations. two unknowns. First equation. So let's move this to the other side. A times expected value of x square. So let me also introduce this. Expected value of x square is, this is equal to variance plus mx square. Am I right? Okay. So this is b times mx is equal to expected value of xy or yx on the other side. This is the first equation. The second equation, a times this minus b times this is equal to my. So this is our equation system. Well, what should I do? Now, solving for b from 2, well, because b is equal to just this, mu y, a, mu x, insert into estimator, then let me write it over here, y is equal to not ax plus b, right, but b is equal to this thing. We get y is equal to ax minus mx plus mu y. Okay. So as you see, I get rid of b. So only one variable is left, a. Okay. So what should I do for that one? Let me use this. Let me see. So for the first equation, then insert b into first equation. I'm trying to solve for a. Okay, so what do I have? Sigma x square mx square a, okay, plus mx, b is this, my, minus a mx is equal to expected value of xy. Am I right? Well, there is some cancellation going on. This cancels this, okay? So mx square, okay. Now I see this a is equal to expected value of xy, okay, then minus mx my divided by, this is a sigma x square, okay. So I get something like that. So how about this? This is, do you recognize this? This is covariance of x and y divided by this. We have studied this in length. Then this is correlation coefficient times sigma x, sigma y divided by this. Then finally I get my a value as, this is correlation coefficient. Okay, correlation coefficient. So you see that this is almost like looking like this Gaussian case, but there is no distributions involved, as you see. Okay, very good. So I get this a value. So what is my estimator then? So this is my optimal a. A, let's say OPT. What is B? OPT is this, but I should insert A over there. Okay. Then my estimator is, optimal estimator is rho xy, sigma y, sigma x, x minus mu x, mx, sorry, plus my. So this is my linear minimum mean square error estimator for y given x. Okay. So I get my estimator, you know, like that. Again, this is terribly like this Gaussian case, but as I have said, we are not discussing distributions in this linear MMSE estimator. The reason is, this is like a parametric estimator. And in this estimator, let me say y hat over here. In this estimator, this is the estimator y hat. So I only need to set these two parameters. Okay. And since error is defined in terms of, risk is defined in terms of expectations, then the moments come into the play, like this variances, correlation coefficients, and so on. So I don't need this density anymore for the linear MMSE estimator. So this is optimal minimum linear minimum mean square error. Okay. So this is linear minimum mean square error estimator. Maybe we don't need this word optimal over here, but just, you know, emphasized one more time. Okay, so let's try to calculate the error. Let's calculate the error. Linear MMSE value for optimal estimator. This one. Okay, so let me see. So let me say this is J mean for A optimal and B optimal, which is equal to expected value of y minus A OPT x, sorry, x minus mu x plus I have B OPT. Okay. And this is parentheses square. So this is y hat, this type of estimator, and I have this. So I should calculate this, but well, let me write this BOPT over here. What's BOPT? B value is my minus AMX. Am I right? So let me include that in this calculation. Then this is expected value of, okay, y minus my. Okay. This is AOPT. Minus AOPT. Okay. X minus, well, this cancels. Is it A? This just cancels. AOPT. Sorry, I made a mistake over here. So this is, sorry, this is equal to X plus BOPT. Sorry for this. So this is general form of the estimator with optimal coefficients. Okay. Now this is correct. So I have AOPT X minus MX. Okay. Is this correct? Okay. Something like that. So I should take the square of this. And this is, if you take the square of this and take the expected value, you get sigma y square. Okay. So how about this? You get the cross term, 2 AOPT, whatever that is. Then you have covariance of x and y because of this cross term. Okay. Covariance, again one more time, plus AOPT square sigma x square. I get something like that. Okay. And how about this? Let me insert it over here. AOPT square is rho xy square, sigma y square, sigma x square, and this one is, okay, so let me erase it, maybe this side first. This part is AOPT covariance of xy. So covariance of xy is sigma xy rho xy times sigma xy, and this is equal to rho xy yx. Is it the case? So if I take this product, this is equal to rho xy square, then I have y square. Okay, I have this. Then what do I see? I see the following. So this part is equal to this part. So this is sigma, so rho xy, sigma y square. Okay, that is that part. And this part is also the same. Both of them are the same. Okay, because x square cancels this x square. I have square of the correlation coefficient times sigma y square. Similarly for this one, both of them are the same. So then I have the final result. Then this thing, J minimum AOPT, BOPT values is sigma y square 1 times 1 minus rho xy square. Okay, that is it. So again, this is the same thing that we have at the end calculated in the previous hour for the Gaussian distributions variance. Okay, so for the conditional variance, you may say, okay, y given x is Gaussian distributed, and this is the variance of that y given x distribution. Well, let me also sketch this. So what do I mean by sketching this? Well, this is my minimum error. Okay, as a function of correlation coefficient, rho xy. Actually, you have seen this sketch earlier. Because correlation coefficient is only defined in between -1 and 1, so I should only sketch this part. Well, it makes sense because otherwise this error would be negative, but that's mean square error. How can it be negative? So obviously it has to be something like this, isn't it? You know, always a positive quantity and so on. So how about this one? Rho xy is fully correlated case is equal to 1. This is rho xy is -1. Again, the fully correlated case. In the fully correlated cases, well, no surprises, we have seen this many times. If there is full correlation between x and y, where are the random variables x and y? So at the beginning of this problem, I have two random variables, x and y. If these two random variables are what we say fully correlated, then I know that from our earlier discussion, let's say y is a linear function of x. So it's already in this form. Okay? So estimator is matching this form, and of course it is minimizing this cost by finding these true values mapping between x and y. Okay? So this is the case when the error is equal to 0. So as you see, actually you have seen this in, let me see, we have discussed this in lecture 12, in our video discussion, lecture 12a, where we discuss, the properties of such estimators. for different correlation coefficients. Maybe at that time we were discussing the meaning of the correlation coefficient. And please check that. At the beginning of that lecture 12a, we have actually seen this graph before. And again, we have discussed similar things. The fully correlated case, almost like fully correlated case, okay? Then your error is, this is J mean. For this case, let's say 1, okay? It's also small. But if they're uncorrelated, if x and y, if they're uncorrelated, I don't know anything about their density, then clearly uncorrelated means this correlation coefficient is equal to 0, isn't it? That is, correlation coefficient is equal to 0, then x, y uncorrelated. So in that case, what is the estimator? Then optimal A is equal to 0. Then your observation is just multiplied by 0. It's just discarded. Then your estimate is just B, meaning that you are discarding the observation and you are saying that, okay, my estimate is just this mean value. Okay? So A is also equal to 0. Then your estimate is mean of Y. So you are discarding all of this information and you are saying that my estimate is just mean of Y. So if that is the case, what is your error? Well, if that is the case, if your estimate is just mean of Y, then obviously this is variance of Y. Okay? There is not much to think about because your estimate is the mean. And this is the definition of the variance. And what we expect is, indeed, this is sigma y square. So indeed, when correlation coefficient is equal to 0, I have sigma y square. So this graph tells us that how well we can predict the other random variable depending on this correlation coefficient between those two. Okay? So this is an important result for our purposes because this is very practical. Meaning that I don't even need the concept of densities over here. If I can set those two parameters, then I am done. I have constructed my estimator. So our topic is how to find these parameters. Okay? So this will be the parametric estimation. Okay, so let me write a few conclusions on this. Let me write it over here. Let me say comments. Number 1, linear MMSE estimators are parametric estimators whose parameters can be optimally set by simply, let's say, calculus. Okay? We do not need PDF or let's say joint PDF. Joint PDF information for optimization, but just the moment, I would explain this immediately in a more detail. The moment information, expectation results, is sufficient to get the optimal parameters. So as you see, this is simplifying our estimator design significantly. Of course, it's not as good as the nonlinear estimator, the general minimum mean square error estimator. It's not as good as that one because of this construction. I am limiting my estimator to this estimator. Okay, what's our second comment? Comment number 2, if, let's say, observation vector x and y are, so this is, again, okay, observation vector, this is desired, are jointly Gaussian, then linear MMSE estimator is the minimum mean square error estimator. As we have seen previously, for the jointly Gaussian case, the minimum mean square estimator is already in linear form. Okay? So if you focus on linear form at the beginning, then you are not losing anything if x and y's are jointly Gaussian distributed. But in practice, where is the, okay, number 3. In practice, we only estimate moments, but not densities in general. Hence, one can say that we assume jointly Gaussian distributed random variables in linear MMSE calculations. Okay? So in linear MMSE there is no discussion of density. But if you assume somehow joint Gaussianity, you are not losing anything. But here is a case. For example, do you remember our this example? This is our earlier example, 1 over 2 sine of x for the estimation of y hat. So this is an estimator like this. One half minus 1/2. So do you think this is a linear estimator? Obviously not, because a linear estimator will be something like this. Or maybe you allow bias, now it will be something like maybe that, okay, a straight line. But clearly, this is not in this form. So what we see is that depending on the density, the performance of the linear MMSE and the performance of the minimum MMSE can be significantly different depending on the density. But in many applications, we have no idea on the density, so we implicitly assume that, or we hope that it is jointly Gaussian distributed. Okay? Then we calculate this linear MMSE estimator. But clearly, we will solve this example one more time with this, linear MMSE estimator, and we will compare performance difference between this estimator and the linear MMSE estimator. Okay, we will see what is the performance difference in between those two. Okay, so we are almost done, but let me discuss the following. So, a simpler and highly recommended vector processing base calculation of linear MMSE estimators. So this is one of our topics. Let me use another marker. Now, I would like to describe the situation something like this. Expected value of y minus y hat of multiple observations x is calculated. Okay. So this is our MSE result. But Let me write MSE. I think linearity will be introduced immediately. Then I'm assuming that this is nothing but a linear combination of observation X. Okay? I think it is clear. So this is W1, W2, Wn. Then I have X1, Xn, and this is nothing but Wk, Xk, K1 to n. Okay? Inner product. So the goal is, by selecting these W linear combination coefficients, I would like to minimize this cost function. Okay? So how can I do this? So let me write the question. So how can we select linear combination coefficients Wk such that MSE is minimized? Okay, so how can we select this? Actually, this is not a very difficult thing to do. Now I am defining J of W vector, and this is as we have done a few seconds ago. This is something like this. Okay. So how should I calculate this? Now, if I take gradient of J of omega with respect to, not omega, sorry, W with respect to W, and equate it to the zero vector. So how can I do this? Okay. So again, I'm considering this. This is like error square. Okay. So this is my error square. So what is this? What's the meaning of this? One more time. This is a partial derivative of J with respect to W1 with respect to Wn. Okay, that's the meaning of that. Now, if I do this, so what do I get? So this is the expected value of gradient of this, very similar as you see, E square. Okay, but this gradient is operating on right now E square over here. So partial derivative with respect to this. So this is 2e times gradient of e. Do you see what's happening? Now, gradient is operating over this e square function. E square is a function of unknown w. So what is the derivative? Let's say the first derivative. Something like that. 2e times e differentiated with, partial derivative of e with respect to w1. And you list all of them over here. Then what do you have? Expected value of 2e. Now, this is my e variable. E is equal to y minus w transpose times x. Okay. So I'm taking derivative with respect to, let's say, w1, I get x1. If I take the derivative with respect to w2, I get, there's a minus sign, minus x1, minus x2. So let me write this, minus x1, minus x2, minus xn. And I'm equating this to 0. Okay. That is it. So let me go over here. Then expected value of e times x should be equal to 0. Okay. Later on, this will be our orthogonality condition. We will focus on this a little bit later. Orthogonality condition for linear MMSE. Okay. But let me focus on this. So this is the condition to be satisfied. Expected value of, so what is error? Error is this. Times x should be equal to 0. Okay. It is the 0 vector, because this is the partial differentiation with respect to n variables, and the results are all equated to 0. Okay, now if I do this, now what do I have? I have expected value of, okay, x w transpose x. I will explain a little bit in a little bit. This is expected value of yx. So this part is easy. Y times vector x, okay, is moved to this side. It's one of in the left side of this equation, okay, over here. On the other side, I have this x vector times a scalar. So this is that scalar. Scalar means a real number, okay. So vector times a real number is here. So this is real number times a vector, doesn't matter. So I can write this one as, since this is a scalar, this is x transpose times w also. If you take the transpose of this scalar, you get x transpose times w. Then from here I get this, expected value of x transpose times w is equal to yx. So I get an equation like that, okay? So this is a trivial step, you may say. This is like a scalar, maybe this is just a number 5. 5 transpose is also 5. So if you take a transpose of this, you get that. Then w, move this w out of this expectation and you have this equation system. Actually, this is what we want to see, because, you know, this is, let me put with this color. This is equation star, let's say, okay, or asterisk. And this equation is very instructive. Well, the reason is, let me write that equation. Okay. So this is what we call autocorrelation matrix. So this is Rx. Okay. So let me call this Ryx. This is also a vector. I will explain it shortly. Now this then becomes Rx linear combination weights is equal to Ryx. Okay. So what's the meaning of this Rx? So this is the autocorrelation of observation vector entries. Autocorrelation, let's say, matrix of observation vector entries. Okay? So this is expected value of x1 up to xn, x1 up to xn, and clearly, well, this is expected value of x1, x1, expected value of x1, x2, and it goes like this, expected value of xn, xn. We have studied this before, something like that. Okay, we have entries. This is what we call this Gremlin matrix, isn't it? Previously we have discussed this. So what you need to calculate is autocorrelation matrix of your observation vector. So autocorrelation matrix of your observation vector is needed on the left hand side. How about this? This is the cross correlation vector of desired random variable and, well, and observations, let's say. So the meaning of this is as follows. Ryx is expected value of y times this x vector, x1, xn. Okay? So it's very easy to remember also. So this is equal to expected value of y and first desired random variable and first observation. Desired random variable and last observation. Okay, this is n. So this is your right hand side vector. So if I can calculate, so this is what I call this moment. This quantity and this quantity, okay, if I can get the numerical values for that vector and matrix, then by simple matrix inversion, I can get my optimal weights. Okay, that will be the linear MMSE estimator, and we are done. Okay, so that's actually very important. Okay, so let me also calculate the minimum linear MMSE value according to this. Okay, so J min of W. Okay, so how can I calculate this? So this is expected value of Y minus W transpose X with W optimal. Okay, meaning that Rx W optimal is equal to Ryx. Okay, so if I set my W according to this equation, solution of this, then what will be this error? Can I calculate this? So it will be again expected value of, again let me call this E. So this is E times Y minus E times, I'm writing E square one more time, E times W transpose X. Okay, so again this is E square, expected value of E square is present over here. Now this term, again I will use this orthogonality, but how can I use it? Well, how about this? Can I move this out of this? Okay, again our vector notation with these bars under the variables is very important, because E is a scalar, as you see. So square of this is error square, and we are calculating the, the expected value of error square. Okay, E is just, this performance related error random variable. So W is constant weights, linear combination weights. I can pull them out. Then I'm left with this. So this is also a vector, but as we have said, this is the orthogonality principle. For linear MMSE, and we have said that expected value of the error and X is equal to the zero vector. Okay, this is actually how we derive this equation. Okay. But this is only valid when E is optimally, error of optimal linear MMSE estimator, obviously, because this does not happen for all estimators, but it only happens when this equation is satisfied, or this equation is equal to this equation. So then this is equal to 0. Okay. Then what do I have? Then E times Y, so this expected value of Y, W transpose X times Y. Okay. So I have expected value of Y square minus W transpose. This is, let me write Y over here, Yx. Since Y is a scalar, I can move this scalar anywhere that I like. Okay, so this is expected value of Y squared minus W transpose, this is a vector, times what we call Ryx vector. This is the cross correlation of desired quantity and observations. So again, in my notation, I'm trying to be consistent. First variable is Y, second variable is X vector, like Yx vector. That is the reason I do this. Okay, this kind of notation. So this becomes our minimum MMSE estimate. I can also, so this is for the optimal. Let me WW optimal, OPT. If I wish, I can also minus. So this is Rx inverse Ryx transpose Ryx. So expected value of y square minus ryx transpose rx inverse transpose. Okay, let's keep this ryx. Actually, since Rx is a symmetric matrix, its inverse is symmetric, so this transpose is not doing anything, so I don't need this transpose. But let's keep it, it doesn't do any harm. Okay, so Ryx transpose. Is this a scalar? Indeed, it's a scalar because this is a row vector, this is a column vector. So this is a scalar, this is a scalar. I'm subtracting scalars. So this is the minimum error value in scalar. Okay, that is very good. Now, I want to do the following, and this will be the last thing for today. Let's revisit the earlier problem with the vector notation. So what was this earlier problem? So I had this y head of x is equal to ax plus b. Am I right? Ax plus b. So let me write this as, this is a, b, and x and 1. Okay? So this will be my, let me say, unknown vector in transpose. This will be my x vector. Okay. So I am interested in, so this is my y head of x. So I'm interested in obviously y random variable of interest. So I want to now use this. Do you agree? So this is a little bit confusing, but x is scalar, x vector obviously contains x as the first element. Now I should calculate this. Now then this equation is, or this equation is, immediately I can do this. Then the optimal weights satisfy, okay, let me write this, Rx, W, Ryx, okay. So can I calculate Rx? Then I'm done. So what is Rx? Expected value of x1, x1. So this is expected value of x square, x, and 1. Then this is equal to expected value of x square is sigma x square, mx square. Expected value of x is mx according to our earlier notation, mx. Expected value of mx is mx, this is just 1. Okay? So how about this, ryx? Then we are done with this first part of this. So I'm done with this calculation. So I'm calculating this one now. Ry of x. So this is expected value of y times, what's my x vector? This. So x vector is just the observations. I'm observing, let's say 1, and I'm scaling with b. Okay? So x and 1. So this is equal to, well, expected value of xy and just my, mean of y. Okay? Now if I write my equation system then, so I'm trying to write this. And this one is this. Okay. So what is W1? W1 is actually A. W2 is B. Okay, so we see that this is the same equation system that we have calculated previously by differentiating with respect to A and B. Okay, but of course we don't need to do it for all the time, because I know the general result. This is our general result. So it doesn't make sense to differentiate it all the time and optimize it with respect to the unknowns, because this is the optimality equation. If this equation is satisfied, then I'm over here. Okay, so that equation contains a matrix on the left, a vector on the right. So if I can calculate this matrix and the vector in one strike, I'm done. Okay, so this is what we are going to do, okay, for the linear MMSE estimation. We'll be calculating this Rx matrix and cross correlation of desired quantity and the observation vector, and that is it. Okay, that will be our main task. Okay, so that's all for today. So we will continue with more discussions next time. Okay, thank you very much.